Hi, we're the multi-agent system team. I'm Emily.
And I'm Joris Blanken.
For our senior design project, we developed a multi-agent system that allows multiple robots to learn and cooperate in order to perform user-specified tasks. Our project involved three main objectives, which are cooperation, observation, and monitoring. The primary goal of this project was to create a system of multiple robots that can perform tasks cooperatively. In order to do this, the robots needed to be tracked specifically using computer vision, which means without the help from technology such as GPS. Finally, we needed to develop a graphical interface that can be used to monitor the system. For this project, we were limited to the use of three main pieces of hardware: the Jetson Xavier NX, a small computer which is used for the majority of system computation, the Jetson Nano, which is a small computer mounted on each robot, and the Jetson JetBot, which are the actual robots themselves. For tracking, we were limited to using only computer vision, which is done by capturing video frames of the robots and their environment and then processing those frames to determine the robot location and rotation. For system learning, reinforcement learning through deep neural networks is needed.
Our system implementation is designed as a big loop. First, frames are captured by the Jetson Xavier NX. Those frames are then analyzed by the state estimation process. State estimation first detects markers located on the robots. The position and rotation of those markers are then calculated, and multiple markers are combined to form one single position and rotation per robot. Finally, the estimated positions and rotations are transformed in order to get a top-down view of the estimated parameters. Estimated parameters can then be fed into the system learning component, which consists of a deep neural network which is trained on use case specific policy using deep reinforcement learning. The system learning component provides the system with specific actions each robot needs to take in order to exhibit desired behavior. Those actions are sent as instructions to each agent over Wi-Fi. The agent computers then receive and execute those instructions. Our graphical user interface features a state diagram to graphically visualize the current position and rotation of each robot, as well as the bounds of the environment the camera can observe, an agent data panel which shows numerical data for each robot, and a live video feed which enables users to monitor the robots. In this demonstration, we show that our system can accurately track individual robots when manually moved around. The graphical user interface reflects the changes to the location and rotation of the robots, both in the diagram and as numerical data. Here we can also see a robot performing autonomously by driving around the origin of the observable area. Do note that this behavior is manually programmed and not learned behavior. In conclusion, we are able to track robots at about 18 frames per second with roughly 2 millimeters of accuracy. Our graphical monitoring system allows users to both graphically and numerically monitor the system and features a live video feed. And our software is able to send and execute 4 different types of instructions, which are move forward 3 centimeters, move backward 3 centimeters, rotate 15 degrees to the left, and rotate 15 degrees to the right.
This project also has some potential future work. First of all, the system needs to be trained. We originally planned to have our system learn some demonstrational behavior, but we were unfortunately unable to due to a lack of time. Another feature that our sponsor, Dr. Wan, had planned is to implement distributed state estimation so that each robot themselves also features a camera and can contribute to estimating state. The This concludes the presentation of our project. Thank you for watching.